Look at my hand, or this pen, or anything around you. The objects in our world are amazingly dense compared to the cosmic average. If my hand was expanded to the average cosmic density, it would fill a sphere that touched the moon. But back in the young million-year-old universe, the matter was incredibly smooth, less than 1% variation in density, and thin, 100 billion times less dense than my hand. And also, everywhere was hurtling outwards, a never-ending expansion. So, how do we reconcile this apparently hopeless beginning with our current happy ending? Some extraordinary things must have happened to bridge these two very, very different scenes. Of course, the full story takes 14 billion years, but the most desperate part, the real struggle to make the kind of universe that we now have, is right at the beginning. Somehow, by just 200 million years, what had been an expanding, thin, hot gas filled with sound waves became a cold, dark universe, sprinkled with brilliant points of light, the first stars. It's really quite an extraordinary and rapid transformation. Actually, if we look at the human parallel that sees 14 billion years as the human lifetime, that 200 million year period corresponds appropriately to the 9-month gestation period. Just as the DNA of the first cell is gradually assembled into a human embryo, so the primordial fluctuations, the cosmic DNA, laid down by inflation, grow over this period, transforming beyond all recognition into the first stars. So the story of how this transformation took place is the topic for this lecture, from sound to the first stars. Here's a diagram that gives you the overall situation. We start with a very smooth, expanding universe, and dotted about are places of slightly higher density. Now, initially, the expansion is both global, the whole universe expands, and local. Even the denser regions expand. But, and here's the key point from last lecture, the denser regions expand more slowly, so the roughness grows, and the patchiness becomes more noticeable. Now, there comes a point when these regions stop expanding and fall back in on themselves. So although the global expansion continues, locally the denser regions have collapsed. And it's within these collapsed regions that the first stars form. This cartoon is, of course, way too clean. Here's a properly calculated distribution of dark matter at about the time the first stars form. Now, we'll talk about all this filamentary structure in lecture 22, but for now, we're focusing on the densest parts that I've ringed by circles. That's where matter has collapsed and where the first stars will form. Now, there's a very important part to the story that I want to stress right at the outset. The road to the first stars involves teamwork, a collaboration, if you like, between dark matter and atomic matter. Dark matter first gets the roughness up to the point that the densest parts can collapse. But they don't collapse far enough, and we need atomic matter to take us the rest of the way to make the first stars. The property that atomic matter has that dark matter doesn't is that it can cool, and this allows it to continue collapsing right up to the point of making a star. Now, one final introductory point. The overall period we'll be looking at, about the first 500 million years, hasn't yet been seen. It's just too far away, the objects are too faint. So I'm going to postpone talking about observations until next lecture, when we'll look at the assembly of the first galaxies in the second half of the first billion years. So let's begin in familiar territory, about 400,000 years after the Big Bang, roughly when the microwave background was made. This diagram shows you just how smooth the universe was at that time. I've sketched, more or less to scale, the variation in density from place to place. The orange curve is for dark matter, and it varies by about 1% above and below the average. So the universe at that time is really quite smooth. But the atomic matter is much smoother. To see its roughness, we need to stretch that 1% way out. Here it is, 100 times less rough than the dark matter, about 100th of 1%. That's equivalent to the difference in atmospheric density between your feet and your head. It's really not much. When you think about it, this makes sense. Remember, it's the glowing atomic gas that makes the microwave background, whose patchiness is exceedingly slight, between about 100th and 1,000th of 1%. Now, the reason the atomic gas is so much smoother than the dark matter is because the atomic gas feels pressure, and the pressure force makes it smooth, just like it makes the air in this room extremely smooth. Now, it's important to remember that the source of pressure is light's enormous brilliance, and the gas only feels this pressure because it's foggy. In fact, we've already encountered exactly how this foggy gas behaves. It bounces in and out of the dark matter clumps. It oscillates as pressure waves, as sound. Now, as long as the gas is foggy and supported by light's pressure, nothing much is going to change, and the atomic gas will remain smooth. Now, you can probably tell where I'm going with this. What happens when the fog clears? Around 400,000 years. From then on, both light and atoms are now independent, and each is now free to move where it wants. Here's our cartoon of the two density patterns. After fog clearing, the atomic matter is now free to move downhill towards wherever the dark matter is denser, away from wherever it's less dense. So the atomic gas quickly gets rougher as it begins to take on dark matter's density pattern. Cosmologists usually show all this using a graph like this, which shows the growth of roughness, delta rho over rho, up the y-axis, against time, along the x-axis, for a particular wave size. Both axes are exponential. There are two curves, one for dark matter's roughness in purple, and the other for atomic matter's roughness in green. Now, remember from last lecture that initially the horizon is small, so everything undergoes superhorizon growth. Dense regions expand more slowly than less dense regions, so both lines increase together at early times on the left. Then when the horizon envelops a dense patch, the atomic matter begins to feel its own pressure, so its roughness stops growing, and instead it bounces in and out of dark matter regions as sound waves, which make these funny ups and downs in the green curve. Meanwhile, dark matter's roughness continues to grow, slowed somewhat by the radiation era, but by the time the fog clears, it is much rougher than atomic matter, just as you saw in the last diagram. But as soon as the fog clears, the atomic matter is now free to move, so it begins to move towards the denser areas of dark matter and away from the less dense areas, rapidly getting rougher. So the green line rapidly increases. By about 15 million years, the two lines have almost joined, and the atomic matter is now distributed almost the same as the dark matter. They are in lockstep. Let's pause for a moment to think about what would happen if the universe didn't contain dark matter. See, in that case, just as before, atomic matter's roughness would get held back until the fog cleared, at which point it would follow this dotted line, normal sub-horizon growth proportional to cosmic size. So, if it starts at 0.01% roughness at fog clearing, even the factor of 1,000 growth from then to now only makes 10% roughness today. Not even close to turn around and collapse. So imagine that. After 14 billion years, we'd still be living in a frigid, dark, sparse universe with just 10% density variations from place to place. Not a single star would yet have formed, and probably never would. Now you can see why dark matter is so crucial at getting the universe on the right path. Because of its independence from light, its roughness can grow at a time that atomic matter is held back by light's pressure. As I've said before, making the first stars requires teamwork. Now, at this point, I'd like to raise a more general question. What was it like back then? From fog clearing to 100 million years is a new period for us. So what might we have witnessed? Well, expansion, as always, continues to redshift the photons. So the light in the universe gets redder, dimmer, and cooler. By 6 million years, the radiation is now almost all in the infrared. So for the first time in cosmic history, the entire universe would be dark to our eyes. So everywhere is pitch black. Not a single photon of optical light remains. And for this reason, this marks the beginning of what cosmologists call the Dark Age. It's a lovely term, partly because it evokes the dormancy and inaccessibility we associate with that early period of European history. Now, although the sky is optically dark, the infrared radiation would still kill you. Actually, it would cook you, since the temperature at that time is about the same as your household oven. It's about 450 degrees Fahrenheit. But as time passes, the temperature drops past water's boiling point at around 10 million years, human body temperature at 15 million years, and water's freezing point at 17 million years. And from then on, it gets colder and colder. A long, dark, frigid night falls across the universe. But within that darkness, a lot is happening. Gravity is gradually working away to increase the roughness. And by about 100 million years, an exceedingly important transition occurs. Although average density regions keep expanding, the densest regions halt their expansion, turn around, and begin to fall back inwards in a collapse. Here are our expansion curves from last lecture that show this nicely. The high-density region is already lagging behind, slowed down by its extra mass. But when we extend this diagram to the right, forward in time, you can see how the high-density region behaves just like a little closed universe, and its expansion halts, turns around, and reverses in a collapse. Now, this diagram suggests the collapse is an exact reversal of the expansion, ending in a dramatic big crunch. But in reality, that isn't quite what happens. Here's a computer simulation of the kind of collapse we're talking about, starting a little after turnaround. The collapse is rather more chaotic, mainly because the regions are not, in fact, nice, neat spheres, so the infalling material heads down from slightly different directions and arrives at slightly different times. Also, dark matter particles don't collide with each other, so they all just zoom back out again. Ultimately, after all the chaos of the collapse, the dark matter settles into a big fuzzy ball that's about half its original size, denser at the center, and sparser further out. These collapsed regions are sometimes called mini-halos because they're a smaller version of the large dark matter halos we find around today's large galaxies, the kind we met in Lecture 9. So here's a slightly improved graph of the collapse with the period of readjustment sketched, along with the final size. Now, a key quality of this kind of collapse is that no energy is released. There's no friction and no light is radiated away. And cosmologists call this a dissipationless collapse. No energy is dissipated. This is extremely important because it means the collapse can't continue very far. And these mini halos only collapse to roughly half their starting size. Now that factor 2 decrease in radius boosts the density by a factor of 8, 2 cubed. And during the collapse, of course, the rest of the universe continues to expand. So when the mini halo finally forms, its density is only about 200 times greater than average, which of course is a significant increase, but it's nowhere near enough to make stars. What we have here are the wombs within which stars can now form. So let's now look at how that happens, how the atomic matter behaves as it gets caught in the collapse of these dark matter mini halos. Well, right off the bat, atomic matter is different in two crucial ways. First, its atoms collide with each other, and this gives the gas pressure, which of course tends to slow the collapse. But those very same atomic collisions can also create photons that leave the system. They might be infrared or light or radio photons. It doesn't matter. They remove some of the gas's energy. So because the gas radiates, it can cool. So its pressure drops. So gravity can pull it down to a much smaller size where it reaches a much higher density. Cosmologists call this kind of collapse collisional and dissipative. The atoms collide to make pressure and they dissipate energy. And these two qualities are crucially different from dark matter. And they allow the atomic matter to collapse much further down and reach the kind of densities needed to form stars. Now, excuse me. Now, ultimately, what gives atomic matter this advantage is that it contains tiny charges, electric charges, electrons and protons. And so when atoms get close, they deflect, they collide. And the jostled charges make photons. See, dark matter particles have no charge. They neither collide nor make photons. Remember, they're dark. So let's now look at some recent attempts to model this combined dark matter, atomic matter formation of the first stars. By now, you should be getting used to the way in which cosmologists work. In addition to making observations and developing physical theories, they also try to calculate what happens on a computer as accurately as possible. Here's one of those computer simulations. As you'd expect, both atomic and dark matter start out very smooth. But by about 100 million years, the dark matter, along the bottom, has collapsed into a few denser mini-halos that form at the intersection of a web of lower density filaments. It's in these denser mini-halos that the first stars will form. Now above, you can see how the gas basically follows the dark matter. Initially, its pressure prevents it from falling into the smaller dark matter regions, so it's fuzzier. But as these smaller regions merge and grow, they are massive enough, perhaps 1 million times the mass of the Sun, to pull in the gas, where its ability to cool causes it to collapse into a very small volume, utterly invisible on this plot. Now this movie shows a zoom into that central clump, starting from a region a few thousand light years across and ending with a region a few light hours across. It's equivalent to zooming into a city to see a single ant sitting on your finger. That final region is roughly the size of the solar system and contains about 200 solar masses of gas moving inwards. Now, at that point, the computational methods hit their limit, but it seems fairly certain that those 200 solar masses will collapse down into a single massive star. Now, these and similar calculations all suggest a single massive star forms at the center of a dark matter mini-halo. The halos are a few thousand light years in size. They contain about 1 million solar masses of dark matter and 100,000 solar masses of atomic gas, and a single star at the center. These first objects are sometimes called microgalaxies because they're about a millionth of the mass of the present-day Milky Way type galaxy. These microgalaxies are dotted around the young universe wherever there were peaks in the original lumpy distribution of dark matter. So a typical separation between two stars might be 10,000 light years, about the distance between the Sun and the centre of our galaxy. These first stars provide what is called first light. The universe ended its 100 million year dark, cold night in a wonderful new dawn, as the light from this new population of brilliant stars flooded out into space. So let's now look at these first stars in more detail. For example, were they like the Sun or other stars in our sky? The answer is probably not. We think they were very unusual compared to today's stars, primarily because their composition was different. They were made from essentially pure hydrogen and helium with no heavier elements. Now, in today's universe, atomic matter contains 1 or 2% heavier elements, things like oxygen or carbon or iron. And even this small fraction significantly changes how stars form and how they live out their lives. Now, the crucial property that heavy elements contribute is an increased ability of the gas to cool. When atoms of heavier elements collide, their more complex electron orbits are jostled more easily, which make photons that can carry away energy, cooling the gas. So in today's universe, a star-forming gas cloud is a very frigid 10 degrees Kelvin. But in the young universe, a pure hydrogen-helium gas cloud couldn't cool below about 250 degrees Kelvin. Now, why is this relevant? It's because hotter gas has higher pressure, and this resists gravitational collapse. So more mass must gather before a final runaway collapse can make a star. Bottom line is, stars born from higher temperature gas are more massive. In the case of the first stars, they're thought to be a few hundred times more massive than the Sun. Now, such massive stars really don't exist in today's universe. Most stars are around the mass of the Sun or less, and a few can reach a maximum of about 60 solar masses. So these first stars were truly unusual by today's standards. So what were they like? Now, you may be wondering, how can we know anything about these first stars? But computer modelling of stars is now a very mature subject. One can actually follow the lives of these massive stars in considerable detail. For example, massive stars are incredibly powerful for the simple reason that their great weight compresses and heats their central furnace, which burns extremely vigorously. These powerful furnaces make the first stars shine with incredible brilliance, perhaps 1 million times brighter than the Sun. So if we were orbiting one of these first stars, it would be as big as your fist in the sky, and the entire biosphere would burst into flames in less than a second. Now, the absence of heavy elements also makes the star's surface very hot, perhaps 100,000 degrees, 20 times hotter than most stars today. And with such hot surfaces, much of their radiation falls in the ultraviolet part of the spectrum. So to our eyes, these stars would appear bluish white. Now, ultraviolet light is extremely destructive to atoms. It can knock the electrons right off them. It ionizes atoms. So these first stars ionize their surrounding gas and heat it up, which has the effect of preventing any more stars forming in that dark matter mini halo. It's a bit like a cuckoo hatching out in some unsuspecting bird's nest. By pushing all the other eggs out of the nest, it ensures it's the only surviving chick. So we think these first stars are loners, born individually. They live out their brief lives, in relative isolation. Again, this is quite unusual compared to stars in today's universe that are born hundreds or even thousands at a time from the same cloud of gas. Now remember, the primary reason these first stars are so unusual is because of their pristine composition, just pure hydrogen and helium with no heavier elements. So let's now look at how that condition began to change, because it did so as soon as the first stars began to die. Perhaps the most important fact about all stars is how they live, how they make the energy that makes them shine. Deep inside the star, nuclear reactions gradually convert hydrogen into heavier elements, things like carbon and oxygen and iron. Now, exactly which elements are made and how fast they're made depends primarily on the mass of the star. Now, these very heavyweight stars have extremely powerful and hot furnaces that burn through their hydrogen fuel at an incredible rate, and within just 1 million years, the fuel is all but gone and the star begins to die. Now, the way in which these massive stars die is one of nature's most spectacular sights. It's a gargantuan supernova explosion that completely disrupts the star and hurls its guts, including all those new heavy elements, out into space. In the case of these first stars, it's thought that the debris may contain 100 solar masses of heavy elements that quickly spread over several thousand light years, polluting, in a sense, the environment. This pollution turns out to be very significant. If those 100 solar masses of heavy elements mix into the surrounding 100,000 solar masses of pristine gas, we end up with about 0.1% pollution. Now, this may not sound very much, but it is, both in human and cosmic terms. On a very bad day, the fraction of smog pollutants in a major city's air is about 0.0001%. If the smog was 0.1%, you could barely see your hand in front of your face. Now, cosmically, this degree of pollution completely changes the gas's ability to cool. This is very important because the next generation of stars to form from this polluted gas will do so from much colder gas, and so all future generations of stars are of much lower mass, much more like the Sun. So the period we've looked at in this lecture is really quite special. It acts as a bridge between the utterly alien realm of the smooth, hot, early universe and the old, cold universe of today with its familiar stars and galaxies. So let's just review how this remarkable transformation took place with these images. The patches on the microwave background remind us that the hot early fireball contained extremely slight variations in density from place to place. After fog clearing, the fireball faded, and with ever deeper darkness, the roughness of both dark matter and atomic gas slowly grew larger and larger. After about 200 million years, the densest parts halt their expansion, turn around, and collapse to form mini halos of dark matter. And within these mini halos, atomic gas cools and continues to collapse, finally leading to a dense core. With only poor cooling available, this warm core undergoes runaway collapse to form a very massive star. These first stars live brief but brilliant lives, which light up the whole universe for the first time since the original fireball. The stars quickly die in powerful supernovae that spew freshly made heavy elements out into the surrounding gas, forever changing the way in which future generations of stars will form. Returning to our human metaphor that sees these first 200 million years as the dark period of gestation which slowly assembles the first structures, it ends, of course, dramatically with the birth of these first stars, which marks the emergence of the kind of universe we now find ourselves in. As we'll see in the next lecture, the newborn infant has emerged kicking and screaming, and the fireworks have just begun.